Welcome to this FMSP online revision video. This is for OCR FP3 and we're looking at the topic of vectors. So we'll start by looking at the specification statements for vectors. The first thing is that you need to understand the significance of the symbols when the equation of a line, and this is a line in 3 dimensions, is written x minus a over p is y minus b over q is z minus c over r. And so this is one way of writing the equation line, and you should be able from that to be able to identify what the vector equation line would be, and we'll take a look at that in a minute in an exam question. The other key thing similar to this is looking at a plane and be able to understand the equation of a plane given in one of these three forms. Either ax plus by plus cz is d. This is a Cartesian equation. This is equivalent vector equation, which says the difference between any general point and a particular point dotted with the normal should be 0. And finally here we've got the vector equation of the plane in terms of a point on the plane and the direction vector of two vectors in the plane. And the other thing that makes this very useful, because this is talking about the normal to a plane, is to understand this idea of the cross product, how we multiply two vectors together and get a third answer which is a vector. You'll have met the scalar product in earlier units. The cross product finds a vector, which is the product of two vectors, and the key thing geometrically is that that is perpendicular to the two vectors we have. And again, we'll look at that in particular in terms of an exam question. You then need to be able to use these properties in a variety of cases. And the best way to do these is find examples and practice all of them. So first of all, determine whether a line lies in a plane, is parallel to it or intersects it. Find the line of intersection of two non-parallel planes. Find the perpendicular distance from a point to a plane and from a point to a line. Find the angle between a line and a plane and the angle between two planes, and finally find the shortest distance between two skew lines. So there's lots of different things to practice. We'll not have a go at all of them in this video, but I strongly advise you to find examples of each of these either from the textbook or past papers and make sure you know how to do all of them. Now the one thing that isn't given in the formula book that's really important is this idea of the equation of a plane written in the form of any general point x, y, z, take away a point in the plane, the dot product of that with n is 0. In other words, if we have some plane here and we have some point here, say this is our coordinate system x, y, z, we've got this here is the vector A, which gives us the position of a point in the plane. The plane itself is uniquely then determined, once we know a point on it, by a normal vector to the plane here, n. So if we know the perpendicular to a plane and a point on the plane, that's sufficient to uniquely define a single plane, and this can be written in this format, or is often more commonly seen r dotted with n is some value d, and here r is the same as x, y, z, the position vector of a general point in the plane, and here's the normal to the plane. So if we do that dot product we will get a single value, and that takes us right back to here, ax plus by plus cz. You can see from this a, b and c are the components of our normal vector. What is given in the formula book, I'll not go through all this now, but I strongly advise you, make sure you got a copy of the formula book, have a look what's in there. Lots of things that you need to know, including things like the plane through the point with position vector A and parallel to B and C has this equation, perpendicular distance of a point from a plane is given here. These are things that you should know how to do, but make sure you know where these values are where these equations are in the formula book and how to find them. So let's take a look at some exam questions. The first one is looking at lines, and then after this we'll do one looking at planes. So we're asked to determine whether these two lines, x minus 1 over 1 is y plus 2 over negative 1 is z plus 4 over 2, and this second one, x plus 3 over 2, y minus 1 over 3, z minus 5 over 4, we want to determine whether they intersect or they're skew. So basically these are two lines in 3 dimensions, and obviously we've got the two situations, either the line here and the line here and they hit each other, or a line here and the line there but they never actually quite touch. So the first thing that's going to make this easy for us, and it's worth stating that with vector questions there's always going to be quite a few ways to do them. If you look at the mark scheme you'll see a lot of alternatives. My approach to this, but it might not be the one that you would use, it doesn't mean yours is wrong, my approach for this will be to turn these into vector equations of the line. So I'm going to start by essentially saying each of these is equal, so I could set it equal to a value lambda, rearrange this first statement here, and I get x minus 1 is lambda, so x is 1 plus lambda. Similarly, y plus 2 is negative lambda, so y is minus 2 plus lambda, and I can put all that together into a single vector equation of the plane, which says that x, y, z is 1, negative 2, negative 4 plus lambda amounts of 1, negative 1, 2. And essentially what I've done here is I've taken each of these equations in turn and rearrange it to make x, y and z the subject. So you can see here, multiply through, we get 2 lambda, subtract 4, I get negative 4 plus 2 lambda, and then put those three statements together in a single vector equation. Applying the same with the second line, I get x, y, z is negative 3, 1, 5 plus, I'll use a different parameter here, mu is 2, 3, 4. Now I want to know, is there a unique value of lambda and mu which would make all three lines of these equations equal? Well, I'll start by solving for x and y. So if I solve for x and y, I've got 1 plus lambda equals negative 3 plus 2 mu. Looking across this line and looking across this line, if my y's are equal, I've got negative 2 minus lambda equals 1 plus 3 mu. I can then solve those by adding them together, and I get negative 1 is negative 2 plus 5 mu, which gives me mu is a fifth. Substituting mu is a fifth back into this statement here, I get 1 plus lambda equals minus 3 plus 2 fifths, so I get a value of lambda is negative 18 over 5. I've done the arithmetic very quickly there. That's not really the emphasis of this video today. I'm sure you can check that and check that you agree with those values of mu and lambda. So the key thing now then is, does this work for z? So I want to now substitute lambda and mu into both of these two bottom lines here. So on the left hand one, for line 1, I get z is minus 4 plus 2 lambda. Substituting in lambda is negative 18 over 5. This is going to equal negative 56 over 5. And similarly, I can substitute mu here into 5 plus 4 mu. And I get 5 and 4 fifths. And crucially, these are not equal. So at the point when the x and the y coordinates of the two lines are the same, the z coordinate is different, so they don't intersect, so therefore they are skew. And that completes the question. Let's take a quick look at where the marks are awarded for this. So, first of all, there's a straightforward statement mark, a B1 here, for actually being able, if we've used this method, as I say, it's worth checking the mark scheme out for this and seeing there's alternative methods. If we use this method of the vector equations of the line, we get a statement mark for this. There's then a method mark for appropriate equations converted from vector equations to simultaneous equations, and an accuracy mark for getting the parameters correct. And then finally here there's a method mark for this attempt to solve for z, and an accuracy mark for the final statement of them not being equal, therefore they're skew. So that's looking at how this way of writing the equation line can be turned into the vector equation line, and how we can use that to solve some problems in 3D vectors. This question from June 2010 looks at vector equations of planes, and also how you can do the normal equivalent of the equation of a plane. So you're told in this question that line L has equation R is -7, -3, 0 plus lambda 2, -2, 3, and that a plane passes through 2 points 1, 3, 5 and 5, 2, 5, and that it's parallel to this line here. So you're asked to do three things: find an equation of the plane and give it in this form, the normal vector form. Part 2, find the distance between the line and the plane, and 3, find the reflection of the line in the plane, giving it a new equation of the line. So a quick sketch of what's going on here. We've got a plane with 2 points in it. We've got a line that's parallel to this plane at same distance away at every point. So we're asked to find this plane, find this distance down to the plane, and then in the last part find a line that's the mirror image or the reflection of that first line in the plane. So in the first part of the question, you're asked to find the equation of the plane. Now you're asked to find it in this r.n is p, and you find it in terms of a normal to the plane. Well, a normal to the plane is going to be normal to two non-parallel vectors in the plane. So we need to find two vectors in the plane. Well, it's parallel to this line, so here's one vector, and these 2 points in the plane, so the vector joining these 2 points is also a direction of the plane. So 1 to 5 is 4, 3 to 2 is -1, and 5 to 5 is 0. So here's the second vector in the plane, and now we can find a normal to the plane by finding the cross product of these vectors, because this will be a new vector that's perpendicular to both of them. Now I'm going to use a method for doing this. Please stick with the one you know. I'm going to stick with the one I know. If it looks a bit odd, just revert to the one you feel comfortable with. So to begin with then, I want to find the top row, so I ignore the terms in the top row, and I do -2 times 0 minus 3 times -1. 0 minus -3 is 3. Then to get the middle row here, again I move down here to 3 and do 3 times by, well there's no number here, so I roll back round to the top there. 3 times 4 is 12 minus 0 times 2. 12 minus 0 is 12. And finally, for the bottom row here, move down 1, that brings me back to the top. 2 times -1 is -2, minus -2 times 4. So I've got -2 plus 8, which is 6. Now this is just a direction vector, so I can cancel it like you would cancel a fraction. It's not essential that you do this, but it will make some of the arithmetic easier. That's the same as 142. So I now know that my plane has got a normal 142. If I do the dot product of this normal with any position vector of a point in the plane, it should give me the same numerical answer. Well, I could try 135 dotted with 142, because I know that 135 is in the plane, and I'm going to get 1 plus 12 plus 10 is 23. So my vector equation of the plane in this format is R dotted with 142 is always going to be 23. and that should work with any point in the plane. You could check it with 525 if you wanted to. Now in the second part of the question, I want to find the distance between L and pi. So I've now got my equation of my plane, and I've got a line here which is parallel to it, so it's the same distance at every point. There's a variety of methods you could use to do this. I think there's about 5 given in the mark scheme. What I'm going to do is use the fact that I know a point on the line. Let's say this is the point I know, -7, -3, 0 is a point on the line, and I know the direction of the normal, because it's a normal to the plane and a normal to the line, so this direction is 142. So I could then work out where does this infinite line going through here cut the plane by finding this point, and then I would know this distance. And actually this ends up being quite a quick method for a reason you'll see in a minute. So this line here that goes up like this, that goes through -7, -3, 0 with this direction, is -7, -3, 0 plus, I'll just use a different parameter, mu, lots of 142. I want to know where this line cuts the plane. That's my question. Where does that cut the plane? Well, it will cut the plane when this dotted with that is 23. So I've got -7 plus mu, -3 plus 4 mu, and 2 mu, dotted with 142 should equal 23, and this is now just an equation in mu. If I multiply out my dot product here, I'm going to get -7 plus mu minus 12 plus 16 mu plus 4 mu equals 23. I can collect all of that together to get 21 mu equals 42, therefore mu equals 2. Now the thing that makes this method so quick is I don't need to now. I could work out this point here by putting mu into this equation, but I don't actually need to, because all I need to know is the length from there to there. Well, this mu is telling me that it's 2 lots of the direction vector, so it's 2 lots of 142. So the length is 2 lots of the length of 142. So the length, the distance, is 2 times by 1 squared plus 4 squared plus 2 squared. 1 plus 16 is 17 plus 4 is 21, is 2 root 21. As I say, there are a variety of other methods you could have used for this, and please refer to the mark scheme here and have a look at some and check that you understand the other ones as well. It'd be really useful revision to do that. Finally then, we want to find an equation of a line which is a reflection of this original line in the plane. Well, if we go back to our method here, we know that this is 2 lots of the vector 142 above this. If it's a reflection in here, it's going to have the same direction, so it's still going to be plus lambda 2 negative 2 3. I just need to find a point on the line. Well, if I know that this distance here to there is 2 lots of 142, to go the same again, it'd be 4 lots of 142. And that's enough to tell me that a point on the new line is -7, -3, 0 plus 4 lots of 142, which is 3, 13, 8. It's going to have the same direction, and that's enough now to tell us that the new line is 3, -13, 8 plus lambda lots of same direction 2, -2, 3. So let's take a quick look at the marks available and how they're awarded for this question. 4 marks for part 1, and in part 1 there's a method mark for identifying both of these two vectors here, and then an accuracy mark for getting a correct form of the cross product. There's a method mark for the cross product and a method mark for identifying the two vectors, an accuracy mark for the cross product, and a final accuracy mark for u equals 23 at the end. In part 2, there's a method following this method, and as I say, please look at the mark scheme. There's a variety of alternatives here for doing this. So there is a method mark for identifying that this dotted with that will give 23, an accuracy mark for multiplying out to get an equation, a method mark for multiplying out and getting an equation, and an accuracy mark for the value of 2, and a final accuracy mark for the last answer. And then in the last part, if you follow this method, there's a method mark for adding on 4, and an accuracy mark for this value here, a method mark for identifying that it will have the same direction, and an accuracy mark for the final answer. So I hope you found this video useful. There are other videos for this unit and for other units on the FMSP website, and please, as I said with those points earlier on, look through all the different techniques that we haven't had time for in this video to practice everything that you could be asked in terms of vectors.